Hello AP Calculus students, Mr. Luya here, and in this video I wanted to go ahead and go over section 8.5 volumes with cross-sections. Currently I'm in the residence of Dr. Lambert, and if you notice any background noise you can just go ahead and blame her for everything. So, yes, I told him to blame you. But anyways, in a previous section, if you think way back in the day with section 8.1, you probably remember that we would find like the area of like this the area between two curves, and we wanted to find the area of that region. And what we would do is we would set up the integral of the top curve minus the bottom curve, and we took that with respect to dx or dy, so on and so forth. Well, in this video, we're actually going to think about, instead of finding the area of a two-dimensional figure, we're going to find the volume of a three-dimensional figure, where this right here is pretty much the base of that figure. And I think the best way of explaining that is maybe giving you guys a visual. So there is a really good website here from GeoGebra, and you'll see that we have the exact same graph over here, right? You can just kind of see that graph, and you can move this around to see the three-dimensional shape. So what's going to happen is we're going to be going ahead and creating a bunch of cross sections with three different shapes, with squares, equilateral triangles, semicircles, and I think the AP Calculus exam is going to ask us to do rectangles as well. So if I go ahead and check off square, what you'll notice is, well, you can go ahead, and what we're going to do is we're going to observe a square as it goes along the entire region between those two curves. Okay, now how exactly is this creating a volume? Well, what's happening is if you'll notice right there, the length of one of those sides of the square is pretty much the distance between the top curve, like you'll see in red, and the bottom curve, which you'll see in blue. All right, so, and obviously the square, it's going to change based on the location on that graph. So the whole point of what we're doing here is, if I went ahead and looked at it from there to there, we're going to be creating a whole bunch of squares. So you can kind of see right there, we're creating, we're looking at a bunch of different squares right there from one endpoint to the other endpoint. And if I kind of create an infinite number of squares, hence the point of the integral. Remember how with an integral we used to do like an infinite number of rectangles with length dx? Well, now we're thinking about an infinite number of squares, and you'll see that if I go ahead and fill that up at least with maybe 100 squares, you can kind of start seeing that three-dimensional shape. Okay? So that's in the case of a square. Well, we can do the same thing with triangles, and we can also do the same thing with semicircles. So that's what we're doing, is we're going ahead and we're going to calculate the area of every single one of those semicircles and kind of bring them together in the form of an integral. So now let me go to our good notes here, and let's just erase all of this. Okay, so going back to my pen, this is my first time making a video with an iPad, so if I'm a little bit slow on this, just kind of bear with me here. So over here, it says the volume of a solid with a known cross-section, it's the integral from A to B of the area of each individual little square or rectangle or semicircle or triangle all throughout the entire curve, where A of x is the area of the cross-section perpendicular to the x-axis. And that right there, perpendicular to the x-axis, is going to determine whether or not we're going to take the integral with respect to dx or with respect to dy if it's perpendicular to the y-axis. So you kind of see what I'm saying over here. So if we think about what the area of a square is, okay, well, you should know that the area of a square is simply going to be whatever a side of the square is and multiplied by itself. So it's s squared. So therefore, the volume of every single little square that's being formed from 0 to 1 pretty much is going to be the integral from your lower bound to your upper bound of s squared dx. Okay? And one thing you got to keep in mind here, well, now you have to think about why did that turn into a eraser? Here we go. What is the length of a side of one of the squares? Well, if you think about it, the length of one of these squares, and maybe just kind of use blue here, the length of one of these squares is whatever the difference is between the top curve minus the bottom curve, right? So we'll call this f of x right there, and we'll call this bottom one g of x. So the length of a square is going to be f of x minus g of x. And that's it. Once we figure out what that is, we plug it into our formula, and we're good to go. With a rectangle, it's going to be a little bit different. This time, the integral of the volume with a cross section, we're looking at nothing but rectangles. It's going to be kind of similar to the square, but instead, it's going to be the integral from a to b of the width times the height. I mean, this is pretty much what we learned in elementary school about how to find the area of a rectangle. But the only thing is, the width of your rectangle is going to be whatever, the same thing, like it's the width of the top curve minus the bottom curve. So we're going to say it's f of x minus g of x. Okay. Now the height, on the other hand, this is I haven't seen too many AP style questions where they make you do rectangles to begin with, but if they did ask you a question about the rectangle, the height will be given in the problem. I'm just going to say given in the problem. All right. So that's about all you need to know as far as those two shapes. And I'm going to show you guys other examples with other shapes. So let's just go ahead and look at example 1. It says a region is bounded by y equals x squared and y equals square root of x and forms the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. What is the volume of the solid? So we're going back and looking at this graph again. So let me go ahead and erase all of this work that I just wrote there. So if I wanted to go ahead and set up the integral where all of the bases are squares, well, I know that this function right there is the square root of x. This one right here is x squared. So if I want to know what is the side length of one of those squares, and hopefully that visual from the GeoGebra website kind of gave you an idea of understanding of why this is a side of the square. Well, we're going to go ahead and set that up. And we're going to set up the integral from 0 to 1. So from 0 to 1 of one of the sides. So the side length of that square is going to be the square root of x minus x squared, right? And you can obviously multiply it by itself to get the area of the square, or you can just square the whole result. Now, I know some of you might get confused and be like, oh, well, what if I mess up and know, which one is the top curve, which one is the bottom curve? I wouldn't stress too much about it, because no matter what, if you square a result, whether it's negative or positive, it'll end up being a positive result anyways. So you go ahead and work out that integral, and you should get 0.1285. And I'll be honest with you guys, for this problem set, I'm okay with you just plugging things in your calculator. What's more important to me is the actual setup of the integral. These integration techniques are things that I'm hoping and assuming that by now you should be good with, and we'll just kind of practice setting up the integrals. That's the important part for this one. So if I look at example number 2, it says let's square cross sections perpendicular to the y-axis. So same two graphs forms the base of a solid, but for this solid, the cross sections are perpendicular to the y-axis, and they are still squares. So if I go ahead and let me just no, I don't mean to highlight. I meant to erase. I'm still getting used to this. So now let me go ahead and do a different color here. Now what we're looking for is this, right? Where one of the base of the squares is perpendicular to the y-axis now. So it's going to be the same principle, except now where with this function was y equals x squared, and this function was y equals the square root of x. We're going to kind of work around that, and we're going to write this in terms of x equals. So it's going to be x equals square root of y for that function. And then for this one, it's going to be x equals y squared. And, by standard convention, when I set this up, I'm going to go ahead and do the right curve minus the left curve. So I'm going to do square root of y minus y squared. So let's go ahead and set that up over here. So I have the integral, again, from 0 to 1, because if I look at my y-axis, it's still from 0 to 1. So the integral is from 0 to 1 of my right curve, which, again, it doesn't really matter, but I like to follow the standard convention of the square root of y minus y squared, that whole quantity squared dy. It actually ended up being almost the same thing That's not always going to work out that way, but in this case it did. So with example 3, this time we're looking at cross sections when no graph is provided. So it is nice to kind of see the visual graph, and then you can clearly see what the bounds are and all of that. But in this case, you don't really know what the bounds are of those two curves crossing each other. So what we should be doing, and let me see if I can change the color here a little bit. I'll do purple. I've always liked purple. All right, so what we're going to go ahead and do here is figure out what those bounds are, and what better way of doing that than just setting the two equations equal to each other. So I'm going to get this part of the equation and this part of the equation, and we're going to make sure that everything is in terms of an x, because it is perpendicular to the x-axis, and they form squares. So let's just kind of use that key bit of information to go ahead and decide. Let's see. Yeah. So I'm going to set them equal to each other. I have x squared minus 4 is equal to 2x minus x squared. All right, I'll add the x squared to the other side. So I have 2x squared, subtract 2x, and then I have minus 4 is all equal to 0. So what I'm going to do here, I can actually take out a 2 out of all of this, and then I'm left with x squared minus x minus 2 is equal to 0. And then when I go ahead and factor that, I have 2 parentheses. Let's see, we have x minus 2 and x plus 1. Nope, let me erase that. Make sure these look nice. Oh, nope. I still have to get the hang of this. So it'll be x plus 1 is equal to 0. So now over here, I know that my bounds are going to be 2 and x equals negative 1. Okay? So when I set up my integral, I know that the bounds are going to be from negative 1 to 2. And now I usually like to do top curve minus the bottom curve, and that can actually easily be determined here, because if you know that this right here is a parabola facing up and this right here is a parabola facing down, it's most likely going to look something like that. So the top curve is going to be 2x minus x squared minus, and then we have the bottom curve x squared minus 4. Now the whole thing, of course, is going to be squared with respect to x. And you can go ahead and plug that in your calculator, and if even if you switch those two around, you'll see that you'll still get the right answer. I'm going to clean this up a little bit. Why did it go back to the eraser? Okay, I'm going to clean this up a little bit, and I'm going to go ahead and change that to the integral from negative 1 to 2. And let's see, I'll write it as negative x squared. Negative x squared is minus 2x squared. Then I have plus 2x. That doesn't combine with anything else. And then I have minus 4 plus 4 plus 4. And then all of that is squared dx. All right. It's always good to practice, simplifying everything with the algebra, just because you'll never know how the multiple choice might phrase the multiple choice answers. So now let's go on to example number 4, where now we're dealing with rectangular cross sections. So it says over here that the base of a solid is bounded by y equals x cubed, y equals 0, and x equals positive 2. Find the volume of the cross sections if the cross sections taken perpendicular to the x-axis form a rectangle whose height is 2 times the width. So again, we're looking at something perpendicular to the x-axis. So if this were to be a rectangle, this is the base of that rectangle, and the distance is going to be from whatever the curve is to the x-axis. So we can go ahead and say, I'll just go ahead and show you. So we'll do the integral from 0 to 2, okay, because that's where it starts and that's where it ends. From 0 to 2 of, let's see, the width of that rectangle is going to be whatever x cubed is minus, and then really that's just going to be 0. I didn't even need to write that, but whatever. That's just so you guys can see it, and I don't feel like editing this. So anyways, that's going to be the width of my rectangle. Now they say that the height of the rectangle is 2 times whatever the width is. So that's really not that bad. You just got to multiply 2 by whatever the width was, which was x cubed, and then dx. All right, so I'm going to go ahead and clean that up a little bit, and I'm going to have the integral from 0 to 2 of 2x to the 6 dx. And there you go. Whatever that value is equal to is going to be the final answer. And then finally for part B, it says find the volume of the cross sections taken perpendicular to the y-axis form a rectangle whose height is 6. So just make sure you read the question carefully, but if I look at this, now I'm going to be looking at pretty much this being the width of the rectangle. So the width of the rectangle is going to be usually the right curve minus the left curve. So it's going to be the integral, and my bounds for y are over here at 0 all the way up until 8, right? Because that's pretty much where the areas in between, or the base of that figure is. So it's going to be from 0 to positive 8. And then the width of that rectangle is going to be the right curve, which is 2, minus the left curve, which is, and we have to write this in terms of y. So I know that y equals x cubed. I know that this was y equals x cubed. So that's going to be x is equal to the cube root of y. So it's going to be 2 minus the cube root of y. So we know that this is the width. And then they said that the height, well, they just said the height was 6. It's not 6 times anything. It's just going to be a regular old 6. And then we're going to take that with respect to dy. So, of course, you can always clean that up a little bit. You can say from 0 to 8 of 12 minus 6 cube root of y and dy. And I'll leave that for you guys to go ahead and figure that out. So I'm going to go ahead and end the video there. I'll probably do this in 2 parts, give myself a little breather and give myself a little break from having to, do this for the first time on my iPad. Hopefully you guys like this new format of doing things. Let me know what you think of it, or if you prefer me going back to the old way. I hope not, because I spent about $1,300 on this system. So just lie to me and just tell me you like this system a little bit more. I'll leave it at that. Take care. Have a good break. Love you guys. Good luck.